We're here today to do a wee workshop session on the oscilloscope. Now, I've taught taking workshop sessions a number of times on scopes, and folk have difficulty because when they look at an oscilloscope, they see that and they see lots of knobs and switches and buttons and dials, and to them, it looks like that. That's the cockpit of an Avro Lancaster, if anybody's interested. In fact, some of the scopes that we're using look more like that. That's a Russian jet fighter where all the instructions, all the things you can read are in Cyrillic and half of them are upside down. And thinking about that gave me an idea that maybe the way to teach oscilloscope use is to teach it if you were the same way as if you were teaching somebody to fly. So that's what I'm hoping to do today. When you're learning to fly, first of all, you learn principles of flight, and then you learn standard controls, not every exotic button, just the basic controls, and then the basic functions, and then the standard techniques. And once you've got all that good stuff together, ready, then you can go on to more advanced stuff. So that's my plan for today, is to do those four areas, but in oscilloscope use. Principles of operation, the standard controls, the basic functions, and standard measurement techniques. And I'm going to do it exactly the same way as if when you're learning to fly, you learn as much as you need to know and no more, and you use one or two techniques, like for example, quick reference cards to make things work easier for you, make it easier to do things without having to go back and start and think about it for first principles, because sometimes you don't have time for first principles. So, starting with the principle of operation, Lee DeForest Kelly is a compound name, a portmanteau of two names. One of them was the doctor on Star Trek, and the other one was the guy that invented the vacuum valve, the vacuum tube, as Americans call it. If I take a glass envelope and evacuate it, take all the air out, and apply a high voltage to it like that, then nothing will happen. It'll just sit there and look at me. There'll be no current flow, there'll be no nothing. If, however, I take a separate supply and heat the cathode, then what happens is that in a metal, the nucleus of the metal atoms are in a matrix. They're in a crystal grid, and in between this crystal grid, electrons are sloughing about. They call it a sea of electrons. And the electrons near the surface, if they're heated, will drift away from the surface. And once they've drifted away from the surface, that negative electrode is going to repel them, and that positive electrode is going to attract them. And that's called thermionic emission. And what happens there is that once the heater heats up, electrons will flow in one direction from the negative cathode to the positive anode. And this is the thermionic diode, the glass valve diode. The next trick that was put in 1850 something was the grid or screen grid. And what happens there is if I put a thin mesh and apply a voltage to it, then by varying the voltage at that grid, I can vary the amount of current that flows between the other two electrodes. Slightly complicated here by the fact that when we're talking about the electrons flowing from the cathode to the anode, which is from left to right in that diagram, the current is actually flowing from right to left. So it gets a wee bit, if you start thinking about currents, it all gets a bit complicated. So now what I'm going to do is take that whole diagram and compress it to the left-hand side of that diagram. And I've now got these electrodes flashing across and going through the anode. But if I leave a little hole in the anode, then some of them will shoot through. And I'll put another anode, which is at a much higher voltage, over to the right, then I'll get a stream of electrons flowing across there, and that, if I make them hit a phosphor screen, can give me a dot. Right? Now what we're looking at here is essentially a small particle collider. This is what you call the Small Large Hadron Collider. Basically, a Large Hadron Collider is two of these facing each other, with the electrons for one being hit by the electrons for the other, and they look at what happens when they collide with each other. Because we're calling them electrons, but when they were first discovered, electrons hadn't been invented yet. Electrons hadn't been discovered, and they were then known as cathode rays, and this became known as a cathode ray tube. And that's basically the tube that the oscilloscope uses, and old television sets used to use. Now, there's some gross simplifications in there. I'm ignoring accelerating anodes. I'm ignoring focusing anodes. I'm ignoring that they have things called suppression grids that they put in to stop electrons from bouncing off and going where they shouldn't. And in a real tube, there's two layers of phosphor, one in the inside of the tube and one on the outside of the tube. But we really don't need to worry about that. As far as we're concerned, we've got an electron gun, stream of electrons hitting a phosphor screen. Now, I can deflect that stream of electrons in a couple of ways. First of all, by a big magnet. Now, I've just put in a sort of diagram there of what a magnet should look like in place. And I've put north at one side and south at the other, and I've made the stream of electrons bend. In reality, if you're doing this in reality, you get right-hand rules and left-hand rules and all that good stuff, and the deflection of the beam would be out of the screen. But I'm not getting into that because life's too short and brutal as it is. So just say that if I put a magnetic field across the glass tube, then I will deflect the electrons to one side. Here's a cutaway picture of a Sony Trinitron tube from about 1970. Thanks to the Science Museum in South Kensington in London for this. This is on display as a museum piece, and I still think that Trinitron tubes are dead modern. How sad is that for me? If you look at the lower right-hand side, you see the connectors, the black plastic thing with the connecting pins sticking out through it. You can then clearly see the electron gun and the various anodes, accelerating anodes, going up to, there's a printed circuit board there called the convergence board. And beyond that, there's what's called the yoke, which is a great big pile of copper wire. And that's the magnetic deflection yoke. And that's what's used to deflect the beam across the screen. The glass has been cut away, as you can see, so that you can see the various layers inside the front of the tube. And that worked for televisions for many of us for a great many years, from about the 1920s through to about the 1990s. So for 70 years, that was the standard of how television tubes worked. You need a great big coil of wire, and that's got its own issues, as we'll talk about in a wee minute. The other type of deflection, which was actually discovered first, is electrostatic deflection. If I put a pair of plates with a separate voltage across them, then that will deflect the beam left or right, up or down across the screen in exactly the same way that magnetic deflection does. The cathode ray tube was a lab oddity. They generally did that. They didn't put the electrostatic plates in, but they did put in a Maltese cross symbol, and they made the electrons, although they didn't know they were electrons, they made the cathode rays cast a shadow on the phosphor. And then J.J. Thomson, Lord Rutherford, in 1897, used this equipment with electrostatic deflection to work out the mass per unit charge of the electron, which meant they'd actually discovered the electron. This is the equipment that discovered the electron 130 years ago. And there's a cathode ray tube. That's a modern Tektronix 5-inch tube. At the back, we have the connectors, again at the top right this time. And then we've got the cathode ray, a cathode gun assembly. And then we have accelerating anodes down to the spot where the tube flares out to the phosphor at the front. The great big thing clicked onto the side is what's called the final anode. All of that area at the front of the tube is metallized inside and out. And the final anode is that metallized area. And on a modern oscilloscope, that'll be at 12,000 volts, so don't lick it. And that wire goes back to the final anode amplifier on the scope. So we've got these two means of deflection, magnetic deflection and electrostatic deflection. Now, the magnetic deflection with a big coil of wire is great if you're only using one frequency. And a television set only works at one frequency. It's going to do, initially it was 405 lines, and then it became 625 lines at 30 frames per second. So it's a very, very fixed frequency. So you can tune the magnetics to do that one frequency. Whereas in an oscilloscope, you want it to work at lots of frequencies. You want it to work at DC, you want it to work at kilohertz, hundreds of kilohertz, megahertz, and it has to work at all of those frequencies. And a set of coils to magnetically deflect like that would be impossible. The electronics to drive those coils would be even less possible. And the other thing is that with a magnetic deflection system, you get what's called linearity issues, where it doesn't always go the same amount across the screen for the same amount of energy put into the coils. And you can fix that. If anybody's ever had to align a TV set, you'll know that you had to take the back off and there was 120 knobs and twiddlers that you had to set up to get the TV aligned. And that was setting up this magnetic deflection system, and it was a nightmare. Electrostatics, on the other hand, will do DC to light, no bother at all, with a simple or simpler transistor amplifier or integrated circuit amplifier. You get a better linear response, you get more, 1 millimeter per volt or 1 millimeter per volt, wherever you are on the screen, but it comes at the cost of having to have a long neck. If you look at that, those two tubes are about the same length. The oscilloscope tube will be about 18 inches long, and so will the TV tube. The problem, of course, is that the oscilloscope's got a 4-inch screen, whereas it's a 21-inch television screen. And that's because of the angle that the actual final spray goes at. In order to be linear, a cathode ray tube doesn't spray over such a wide angle as a television did. And so you get a 90 degree or a 130 degree television tube, which means the television receiver is much smaller front to back. Remember, TVs used to be quite big, but they weren't that big front to back. And very often the back had that sort of Paxland bubble sticking out the back to accommodate just that wee bit. The rest of the electronics wasn't that big, but the tube was the issue. Cathode ray tubes, on the other hand, if you get a cathode ray oscilloscope like that, it's going to be 2 foot from front to back, even though it's only got a 4-inch screen. In recent years, we've also come across simulated oscilloscopes. These come in two flavours. A standalone digital scope, which is the size, shape and weight of a handbag. It's about 1 foot across and maybe 8 inches high and maybe 4 inches front to back, and it's got a handle and it looks like a handbag. In our house, that's how it's referred to. Where are you going with that handbag? But that's my wife. She's got some very funny ideas about herself. And then the other one is an oscilloscope peripheral for a PC. And that's a little box of electronics that you plug into your PC and use your own PC as the oscilloscope. And that's what the handbag looks like. It's got a lot fewer knobs and switches and stuff because they tend to use either on-screen touch displays or soft keys. You know, the buttons down the side that, depending on what you're doing, the buttons have got a different function. When you're setting up the trigger, they do one thing. When you're setting up the gain, they do another thing. The most recent ones, Rigol have got one. By the way, you can buy these things from about £250 to about £25,000, depending on what you want to spend. Rigol have recently brought one of these out that's a 12-bit oscilloscope, but it's only an inch and a half thick, so it'll live on a swinging arm. You know that the arms for supporting monitors, it'll live on one of those above your bench and you can push it back out the road when you're not using it. Essentially, it's a PC that's got an analog front end on it and a digital front end for the switches and knobs, and a screen that's dedicated to being an oscilloscope. But actually, all that's inside it is a robust little PC. The simulators, there's a simulated device. I've got one of these and I use it daily practically. It has got so much more going for it than the oscilloscope, but it's a wee bit harder to learn and it's got some drawbacks. It works on your screen. So if you've got a great big computer screen, you've got a great big oscilloscope screen. If you're using a tiny wee laptop screen, you've got a tiny wee laptop oscilloscope. There's what the display on it looks like. All the functions of an oscilloscope are there, but it's maybe a wee bit harder to understand. The other thing about it though is that that device, as well as an oscilloscope, does lots of other things. So which one do you need, or which one to choose? The old-fashioned, the big analog scope is easy to use. It's very cheap if you can get your hands on one, and they're great to learn on. They're very robust, they're very forgiving. You're not going to get hopelessly lost and get fed up and wander off with an old-fashioned analog scope. The digital scopes are also cheap. They're smaller, so they take up less bench space. They can get tucked away. You can tuck a scope away into a cupboard or a drawer. If it's a wee digital handbag, you're not going to do that with a big Tektronix or whatever. Slightly harder to learn on because they can be a wee bit idiosyncratic. Each one's got its own rules, and so it's a wee bit more difficult to learn on. The simulator is dead cheap. It takes zero bench space because it's the size of a cassette, essentially. And it includes other tools. One of the big drawbacks is if you buy one of these and it's for Windows 7, then it might not work in Windows 11 because the software might not be available for Windows 11. This is just the hardware, and all the cleverness is in the software. So you have to make sure you get one that the software is going to keep up to date. This one, the Digilent that I use, is been outdated. Mine was a Digilent 2. They're now at the Digilent 3 and Digilent 4, but they still support the Digilent 2. Which takes me to the other thing, that the Digilent ones also have a hardware-free option. There's the opening screen for my little waveforms thing. Down the left-hand side, you will see there's a scope, there's a waveform generator, there's power supplies. I can use it as a voltmeter, I can use it as a data logger, I can use it as a logic analyzer, I can use it as a digital pattern generator, I can use it for static I/O to drive a 7-segment display or an LCD display or whatever. I can use it as a spectrum analyzer, a network analyzer, an impedance analyzer, a component tracer. It has all sorts of stuff going for it in that wee box of tricks, and it's all done by software. And the device manager is now open, and there's I think there's 24 devices that it supports. But one of the devices that it supports, the one that I've currently selected there, is the sound card. You can download this software. It's called Waveforms by a company called Digilant. You can download it for free, which is my favourite price. And if you start it up, even though you don't have any Digilant hardware on your PC, it'll let you use the sound card as both a twin channel scope and a twin channel waveform generator. So that's you get a signal generator and a scope for nothing. All you need to supply is a couple of 3.5mm jacks to go into the sockets on the side of your PC or the side of your laptop to give you the connections, and it's there for nothing. So I'm a big fan, as I say, of the simulated scopes, but when I'm working, I tend to use a real one. Now, before I get any older, I have to address this. Earths and grounds should be the first thing you think about when you're doing any kind of testing. Is you should always make sure you've got your earth to fall back on. If you've got a scope, any kind of scope, then the earth pin on the kettle plug that supplies the scope will be connected to the chassis of the scope to avoid noise. These things are very prone to the slightest wee bit of electrical noise. And so it'll have a good earth wrap around all the way around. There'll be a Faraday cage that's earthed all the way around the internals of the scope. The case of the scope is earthed. The BNC plugs that you connect your scope probe to are earthed as well. And if you connect the scope probe to any circuit, you are earthing that circuit. And you have to think about that. The reason that I'm mentioning it is one of the simplest things to do is you think, okay, I'm going to put my scope onto the track and see what's happening with this DCC signal. But a DCC signal is one of the tracks goes positive with respect to the other, and then the swap over, the other track goes positive with respect to the one, and back again, whatever it is, 15,000 times a second. Neither of those tracks is earthed. And if you connect your scope probe to it, if you connect it to one side, you'll just see a load of noise. And if you try and connect the crock clip of the scope probe to the other track, what you're doing is shorting out your DCC controller. And your DCC controller might not appreciate that. The H-bridge in it in particular might not appreciate being shorted to ground. And you can cause smoke and disappointment in equal measure, and you don't want either of them. So be very, 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 very careful with your earths when you're using the oscilloscope. Now, you can get round about this in lots of ways. First of all, you can float your circuit. What I do is if I'm working on a circuit, I tend to have the circuit sitting on the bench and I'm using a 12-volt power pack made up of three 18650 batteries and a little jack. And there's no earths there. So the one earth in the whole circuit is the one in the scope. And when I connect it to my circuit, I'm earthing part of the circuit, but I'm not earthing it to earth. The power supply that I'm using is independent of the oscilloscope. You can isolate it either using a transformer, optical isolation, opto-isolators and all those good stuff, or other magnetics. There's other magnetic ways of doing isolation. You can buy a specialist isolating probe if you've got money. And if you've got money, leave a comment in the comments for this and you can adopt me. Or as a very last resort, you can float the scope, and I do not advise floating the scope. That's actually disconnecting the earth wire to your oscilloscope. For one, it will cause short circuits anyway, but it also means you'll get huge amounts of noise in the oscilloscope because that Faraday cage that was keeping the noise out is now an antenna picking up the noise and transferring it to the scope. So I would never ever really do that. Just as an example, there's three things there, some circuit that we're working on. And XA, XB and XC are things. They could be transistors, they could be an H-bridge, they could be a stepper motor winding, they could be whatever. And I've decided I want to look at what's happening across XA. Now, if I just put my scope there, then that crock clip is connected to the ground in that oscilloscope. And the ground in that oscilloscope is connected to the ground of that circuit. And so I've effectively shorted out XB and XC. Now, XB and XC might be the transistor that's driving this, or they could be, whatever it is, they could be the resistor that's stopping it from passing a lot of current. But either way, they're no longer in circuit, they've been shorted out. And at the best, this circuit won't be doing what it's intended to do when I put my scope on it because of that short circuit. At worst, I've shorted out the supply and I'll blow the supply up, or I'll fuse tracks on the printed circuit board or whatever. There is a solution. It's not for this today. We'll maybe do a more advanced oscilloscope course sometime. But there is a solution here whereby I can take two channels on my oscilloscope and put them at either side of XA, and then tell the oscilloscope to take the difference in the two voltages. And I'll get what's happening across XA without shorting anything to ground. But that's not for here. So there are ways of doing it. But just please, please, please think about earths. So, on to the standard controls. And at this point, the animations that we paid all the extra money for start to kick in. The first and simplest, two deflection plates either side of the screen, connected to the Y amplifier. The Y amplifier takes a small signal, makes it very big, and applies it to the plates. And when it does, the beam gets deflected up and down. Similarly, another pair of plates at either side of the CR tube. And again, when we apply a signal, it gets deflected left and right. Now, if I've got a spot right plumb bang in the centre of the screen, like that top left image, then what's happening is there's no voltage applied anywhere. And the spot will stand still right there. If you look at the top right, I've applied a voltage to the Y plates and it's deflected the spot up the way. And I've still just got a spot. If you look at the bottom left, I've now got a line between the centre of the screen and the top. So there's a voltage applied to the Y plates, but it's going from 0 volts up to a certain voltage and back down again. And as the voltage goes up and down between 0 volts and whatever this voltage is, the spot follows it, and so I get a line. The bottom right is an AC voltage applied to the Y plates. The spot goes up and comes down and carries on down through 0 to a negative value, and then comes back up and just carries on up to the positive value again. And so just from that, I can see that there's an AC voltage. Don't know an awful lot about the AC voltage, but just for looking at the spot and remembering that that spot's being deflected by the voltage, I can learn quite a wee bit. Here's some more complicated ones. I've now got a voltage on the Y plates, and I've also got a voltage on the X plates. So top left, the voltage on the X plates equals the voltage on the Y plates. So as it goes positive X, it goes positive Y. And it both go 3 squares on that display. You notice there's a thing called the graticule with all these wee squares on it. And it goes 3 to the left and 3 up, and 3 to the right and 3 down. So I've got the exact same signal on the Y plates that I've got on the X plates. Top middle, I've got the exact opposite signal, so that when the X goes up, or rather the X goes to the right, the Y is going down. And now when the X goes to the left, the Y goes up. So what I've got here are two signals that are the same size, because it's 3 divisions in each way, 3 by 3 and 3 by 3. So they're two identical sine waves or waves of some description, but they're exactly out of phase. When one's positive, the other one's negative. If I put the two lines of a DCC signal on my oscilloscope, or rather, one in the X and one in the Y, that's what I'd get. I'd get to see that would be what a DCC signal would look like. The circle, top right, is when two signals are 90 degrees out of phase, which means that when the one signal's reaching the peak, the other signal's at a minimum. And when the next signal goes to a maximum, the next one gets to a minimum, the other signal's at a maximum again. Looking at the bottom one, things are now getting slightly more complex. The bottom left is the same as the top left, except the X is only going 1.5 centimetres for 3 centimetres on the Y, which means the signal on the X plates is half of the signal on the Y plates. The next one, middle at the bottom, is the opposite. This time the X is going 3 for 1.5 on the Y. So the Y signal's half of what the X signal is. And then lastly, in the time it takes the X to go from left to right and from right back to left, the Y has been up and down twice. So that one there tells me that the Y signal is twice the frequency of the X signal. And because the Y signal's gone up and down 2 centimetres and the X signal's gone up and down 3 centimetres, I can see that the Y signal is twice the frequency and 2/3 the amplitude. So this, just from looking at the spot on the screen without any of the knobs, I haven't touched a knob in this oscilloscope yet, I can tell a lot of information. But this stuff is really, really advanced. You don't have to know this stuff. You don't have to be able to do this stuff. But once you've done a lot of this, you've played with your scope a lot, you'll start to learn to interpret things like this. Let's go back to that amplifier, the Y amplifier. There's not an amplifier with a gain that says 10, 100, 1,000, so that you work out how many volts you're putting in and how many thousand you have to multiply it by to get the deflection. None of that. What happens is it's already calibrated. If you look at the knob there, the outer part of the knob, there's a white stripe that's currently pointing at 2 volts per division. That means that the internal amplifier is set to whatever number, 18,407, that it takes to make the spot move 1 division for every 2 volts you apply. Also, if you look at the knob, the highest value there is 5 volts per division. And there's 8 divisions in that screen. So the biggest voltage I could apply to that oscilloscope would be 40 volts. Right, 5 volts per division, 8 divisions, 40 volts is going to take me over budget. The input is rated at 10 times that, at 400 volts. And as we'll see in a little while, there's a trick that you can do with scope probes to get a higher voltage on. But you really have to be aware that you don't want to go over either A, what the oscilloscope can take in terms of voltage, and B, what the oscilloscope settings will give you. If you set it to 5 volts per division and put 200 volts in, then you'll not be able to see it. It'll be 5 volts division, 200 volts is 40 divisions up or 40 divisions down. You ain't seeing that. You've only got 4 divisions up and down. So you'll not be able to see it. So you have to bear that stuff in mind. There's also another part of the input circuit that's really important, and it's a switch. And it says GID, AC and DUC. Ground, AC and DC. Now, people assume that AC and DC stand for alternating current and direct current, but they don't. DC stands for direct coupled, and if you look at the diagram above, you'll see that if the switch is in the direct coupled position, then the signal goes straight through a wire through the switch and into the amplifier. If I put it in the AC, or alternately coupled position, then the signal goes through a capacitor through the switch and into the amplifier. And if I put the switch in the ground position, then the input is grounded. Now, I need to talk about at least two of those. The DC one's pretty intuitive. You connect the signal to the amplifier and things happen. That's great. The AC one, I've said it goes through a capacitor. Now, the capacitor isn't just a simple capacitor. Usually there's some clever electronics there instead of that capacitor. But what it does is a capacitor lets a changing signal through, but blocks any DC component to that signal. So if I've got a 5-volt signal with a little bit of ripple on it, if I put it through a capacitor, the capacitor will let the ripple get through, but the 5 volts won't get through the capacitor. And that's what that alternate coupling's for. It lets you, if you've got a tiny signal built onto the top of a big solid 8 DC signal, it lets you separate the two out. It lets you not see the DC component of the signal you're looking at. And the ground connection, why the ground connection? Well, that's to let you see where 0 volts is on your display. So far, I've always said that 0 volts is at the centre of the display there. But it makes more sense to move the 0 volts down a wee bit to the bottom of the display so I can see more information. I can turn up the sensitivity and get more detail. So in order to do that, there's a thing called the vertical positioning knob. And the vertical positioning knob lets me move the spot up and down before I amplify it, so that I can get a 0 volts line that's near the bottom of the screen. And then once that's done, I can apply the signal and see what we're getting. Over in the x-axis, there's a time per division knob of some description. I've used different knobs here off of all sorts of different oscilloscopes. I'm not settled on one particular model. They've all got these. This is the standard stuff that has to be on all of them. And when I talked about the X amplifier moving the spot, I talked about that, where the X amplifier is connected to the signal and it moves it left and right. The knob with the time per division on it actually produces a saw wave. Now that saw wave moves very slowly from a low voltage up to a high voltage and then snaps back to the other side. So my spot goes across, and as it gets to the far side, it snaps back. While it's snapping back, you don't want to see it. So some of the electronics will also suppress the flyback, as it's called. That line, when the line's flying back, you don't want to be looking at it. So I can take that line, and as the time base throws the spot back across to the left, I can switch the spot off. Some scopes have actually got a Z input on them, and you can modulate the brightness of the beam yourself, but they'll always do this automatically. They will suppress flyback, and you will get that, so that your scope is now tracing that waveform, and every time it gets to the right, it's flying back to the left, but you're not seeing it flying back. And that brings us to the next area, and this is where the magic lies. If you ever teach this subject, you will spend more time doing this next wee bit than you will doing the rest of it together, and that's triggering. There's a sine wave showing up on my oscilloscope, and you'll notice that that sine wave starts at exactly the centre of the graticule over at the left-hand side. It starts at the left-hand side, right at the centre. It goes up, it goes down, it goes up. It starts coming down again, and it's run out of screen. So it flies back. And it will fly back to that point. And it will continue displaying. And this time when it gets to the right-hand side, it's away down at the bottom of the graticule. And when it flies back, it'll do that. And you end up with this spirograph display, as I call it, on your screen. Because the same wave keeps getting displayed, but it keeps getting thrown from a different point on the left-hand side, because whenever the spot got back to the left-hand side, it just kept tracing. So in order to stop that from happening, we use what's called the trigger system on the scope. And this is quite complex, and it's unique to the scope. Every scope that you've got will be slightly different in this, but they've all got some common features. You can decide which trace you're triggering on, and you've got 2 or 3 basic modes. In automatic mode, or auto mode, this is currently on, as you can see, lit up. I've got auto and channel 1 and positive. And so that means that when the trace gets back to the left-hand side, it will just automatically start again. And if it automatically starts again, I get my spirograph. If I put it to normal, then in normal mode, what happens is there's a level knob there. You see at the top right-hand side, level. And that level knob, it doesn't have a number on it. You can't set level 3 or level 7 or anything. You just have to twiddle it and see what you've got. And basically what that does is it picks the level on the left-hand side of the screen that the trace starts at. So now my trace, when it gets to the left-hand side of the screen, it will wait until it gets to that point right in the centre, and then it'll trigger. And when it comes back, it'll wait again, and then it'll trigger. And because it's always triggering at the same point on the screen, the traces always go over the top of each other. And so instead of the spirograph, I get the signal tidied up, always the same. And if I adjust the trigger level, let's turn the trigger level up a little bit, then it'll trigger further up the waveform. And if I turn it down, it'll trigger lower down the waveform. Lastly, there it's triggering at that point, which is the centre of the waveform, and it's triggering automatically on channel 1. If it's triggering at the 0 point, where the graticule crosses the waveform there, then there's at least 3 spots where it's at 0. So I have to tell it that I want it to trigger when it's going positive. You see I've got slope positive there. So it's going to trigger at slope positive at the 0 volts point of the waveform over at the left. And if I was to switch that slope from positive to negative, then it will trigger at the same spot, but this time it triggers when it's negative going. It's worth taking your oscilloscope and a simple signal generator and playing with triggering for half an hour on your own, knowing that you can't make mistakes, it's not going to matter, and you will learn an awful lot by learning about some of these modes. As I explained a second ago, if you put it on automatic mode, then as soon as the spot flies back, it will re-trigger. And the spot will always be visible on the screen, and you'll get that spirograph effect with dozens and dozens and dozens of instances of your waveform all appearing on the screen all at the same time. You click it into manual mode, then you pick the level and whether you want it positive going or negative going. And generally what you'll have to do there is twiddle it to get the trace. A thing that you'll find happens is you put it into manual mode and you get nothing. And the reason you get nothing is that the level is set too high or too low for your waveform. So you just adjust the level, and as you bring the level down, it'll catch the trigger and suddenly the thing will appear. And as you keep turning the level, the trace will seem to move left and right. It's actually the re-triggering point that's moving down or up the trace over to the left-hand side. You can also use it in single shot to cap, which means it just waits for a single occasional event. Either you trigger it by pressing a button or it triggers by getting a signal through a BNC connector. Or you can trigger them at line voltage, which is 50 hertz in the UK, and that's great if you're working in main supplies or television sets where everything's 50 hertz, then you can make it trigger at 50 hertz all the time. If you've got a digital scope, then you can delay the triggering, in which case the trigger isn't over to the left-hand side of the screen, but the trigger point is in the middle of the screen somewhere. And that way you can see what happened just before the trigger happened. So if I've got a detector and I've got the scope watching the detector, I can also have another trace watching what happened, let's say, to the totty just before it triggered. Was the totty rising? Was the totty falling? Was there noise in the totty? And if I want to see something just before triggering happened, then delay is useful for that. And there's also an external option very often, whereby you can trigger the trace to appear by putting an external signal in. Now, one of the tricks, if you've got something like SPI or I squared C, where you've got two signals, like a clock signal and a data signal, but you want to see it on your two channel scope, but you want to trigger it, you can either trigger it on the first occasion of the clock going low or whatever, but if you've got external triggering, you can also use the external trigger as an invisible trace, whereby when the chip select goes low, that triggers the scope, so that every time this circuit gets started or your chip gets selected, the scope comes on and you can see what's happening. So effectively you've got a third trace, but you can't see the third trace, but you know what's happening on it, so you can use it to trigger. Now I've talked about double trace oscilloscopes, and if we go back to this, there's no way that I can do two traces with that. The electrostatics won't allow two streams of electrons, so I can't have two traces appearing through that arrangement. However, if I look at my scope controls, there's this called chop and alt. And what that does is clever electronics will measure your two traces from two amplifiers. You've got two Y amplifiers, and it will then move the spot to where it should be for each of the two traces. And it can do it in two different ways. It can either, first of all, draw one trace and then draw the other trace, or it can draw a little bit of the first trace and then a little bit of the second trace and then a little bit of the first trace and a little bit of the second trace. The first one, called alternate mode, alt mode, is brilliant if you're working at high frequencies. If you're working at high frequencies, the fact that your two traces are a few nanoseconds out or a few microseconds out with each other won't matter. Whereas if you're going really slow, the fact that you only see one trace and then you see the other trace and the first one's disappeared and then it goes back to the first one and the second one's disappeared, working slow, alternate mode's no use to you. Oppositely of that, in chop mode, if you're using your scope very, very fast, then chop mode is no use to you because you can see the chopping taking place. Right? And you get these chopped up waveforms. Scope that I use all the time is a Tektronix 2445. And if you look, it's got four traces. There's four different, there's a very fast sinusoid, and then there's a square wave, and then there's a medium fast sinusoid, and then there's a slow sinusoid. Four traces, plus it's got two traced bits of text. The one at the top there, with the details about the time base, and the one at the bottom there with details about the amplifiers. Six different traces, all on the one screen, and it's usable because of the clever electronics inside the scope that's switching between there is only one beam of electrons, but it's moving about and painting that screen very, very fast. Now I want to talk about probe compensation. Remember, what we're talking about here is each of the major control groups. This is the second last one, you'll be glad to hear. If I have a signal, that's a signal off a little microchip board, and it generates a signal for a servo, and it looks like that. And I would like the scope to have a picture on it that looks like that, with the signal that's driving the servo. However, if I just connect a big lump of wire between my scope and the output in my circuit, then what will happen is when that signal goes high, it'll have to charge that cable. That cable's got capacitance and inductance, and current will have to flow to let that capacitor come up to the right voltage, or for that inductor to overcome the change in voltage. And so I'll get something on the screen that looks like that. And I'll get distortion, and the distortion has been introduced by the piece of wire that I've connected between the circuit that I'm testing and the oscilloscope that I'm testing with. So I use a scope probe. And if I use a scope probe, as long as the scope probe's set up properly, then I will get the signal that represents what's coming out of the device under test. Now, in order to set the scope probe up, somewhere on the front of my oscilloscope, there's a little thing called a calibrator. And what I do is I put the scope probe onto the calibrator, and I use a little non-metallic screwdriver, usually comes with the probe. And there's a little variable capacitor inside the side of the probe. And by twiddling the probe there, I can twiddle it until I've got a square wave. You can see where that one there is still needing a little bit of adjustment. It's overshooting both high and low. So I've got to twiddle it a wee bit more till it turns back into a square wave. What it does is it puts a square wave out that's running at the same frequency as the time base. So that if I'm looking for a 1 megahertz signal, I attach my probe and calibrate it against a 1 megahertz signal. And that way I know that I'm going to be seeing on the scope what I think I'm seeing on the scope. In order to do that, I have to put that little bit of circuitry into the scope probe. And there's the scope probe there. And I have to twist that little C1 to make the signal right when it gets to the scope. But in order to do that, there's losses. The voltage getting to the scope will be less than the voltage at the device under test. DUT, by the way, is device under test. And so the voltage at the scope is going to be less than the voltage coming out of the device under test. So what I do is I make it a feature, and I set up R1 and R2 so that the voltage at the scope is going to be 1/10 of the voltage at the device under test. So that way, if it's 10 volts at the device under test, it's 1 volt on my scope. So if I read 1 volt on the scope, I can actually read that as being 10. A lot of modern scopes, you can tell them that you're using a 10-to-1 probe, and it'll actually do the conversion for you. It'll add the 0 on. But failing that, if you've got an older scope, you maybe have to remember to add a 0 on. And so if you're using a scope probe, you have to calibrate it, and you have to remember that it's a 10-to-1 scope probe. Some scope probes have got a switch on them, 10-to-1 or straight through. If you go straight through, then you lose the trimming of the trimming capacitor to make your scope probe linear. but you do gain the fact that the voltage at the scope is the voltage at the device under test. And while we're talking about probes, there's umpteen other types of probes. You get active probes, you get proprietary probes, made by Tektronix and Rigol and all these people. You get differential probes for measuring the difference between two signals rather than an absolute signal. You get ones for doing high voltages, you get isolating probes, there's umpteen of them. That there's a Rigol oscilloscope, and as you can see, you can just plug a BNC into it as normal. But if you've got the special Rigol probe, then when you plug the BNC in, all these other connections get made, and your scope probe has got amplifiers and logic and all sorts of stuff on it, and you can do other things that you can't do with a more conventional oscilloscope probe. Most of those other scope probes, by the way, are big, big money. So that's us finished with the control groups. The tube control group contains brightness, focus, astigmatism, brightening up the scales, the graticule, and a thing called the beam finder. If you've got an old analog scope, there'll be a button on it called the beam finder. And what that does is it turns the beam on, it turns down the Y amplifier, it turns down the X amplifier, and puts the beam on the screen so that you can see it, so that you know that your scope's working, and so that you know where it's flashing off to, what's turned up too high. And the beam finder's a great thing. You press the button and the beam appears and you know that your scope's working and you've made a mess of something. The Y amplifier we've talked about, volts per division, where it is on the screen, and DC-AC ground. If you can remember those three, those are your memory items, you're golden. Time base, which is also the X amp, but we don't use it as an X amp really. Time per division and the X position, you can move things left and right a little bit, but the time per division is all really that the time base is about. Triggering, I spent a bit of time on triggering because you have to spend a bit of time on triggering. Your own device, your own instrument, play with triggering for half an hour and you will learn it. And then the calibration I just mentioned for calibrating your probe and finding out how it works. Now, if you look at any oscilloscope, right, this is my personal favourite one. If you look carefully, you'll notice that down at the bottom left, there's all the screen stuff, the beam finder and the focus and the intensities and the illumination, and it's all got a wee panel round about it. You see it's all in the one wee panel. And if you look in the centre there, the vertical stuff has all got a wee panel round about it. There's a wee box drawn on the screen to let you know that that's where the vertical stuff is. Over to the right, there's the triggering in its own wee panel as well. They always draw a wee box round about controls that do the same thing. Right? All these things that I'm talking about are grouped, and you're always grouped together and always get a wee panel round about them. Here's the ham egg, and again, there's the panels. For below the screen, you've got the intensity in the beam finder and power and all that good stuff. And then there's the volts per division and the time per division, all in their own wee panel. There's a Rigol handbag, and again, you can see all the soft keys round about the screen on that one. But if you look just to the right of the soft keys, you can see a panel for Y position and Y scale. You can see the horizontal panel with the horizontal position and the horizontal scale. And you can see the trigger panel with trigger mode, trigger menu, force triggering, and the trigger level all in that wee panel. And that's how it's worked. Notice the panels. Look at the front of the scope. You probably never, if you've maybe been using a scope for years and never noticed that all these things have got these wee panels drawn round about them. So finally, we move on to what the scope's going to do. We're going to talk about measurements techniques, and I'm going to stick with this aviation analogy. The scope can measure voltage or voltages. It can measure time, and from time you can work out frequency. The oscilloscope won't give you frequency. It will give you time, period. Right? Now, if you've got something that happens in a tenth of a second, then it's happening 10 times a second, so the frequency is 10 hertz. So it's very easy to convert time, period, to frequency, but the scope's measuring time. You can look at waveforms, obviously. You can take the difference between two waveforms. You can look at occasional events, things that are happening only now and again, and you can look at things that only happen once. The scope cannot directly measure continuity, or current, or resistance, or capacitance. It can't characterize semiconductors. It can't do fault finding, and it doesn't understand CAN or DCC or any of these things. However, the optimal thing that I've written in that slide is the word directly. Because although you can't do these things directly, you can do an awful lot of them indirectly with a scope. Let's say, for example, I want to measure current. There's a pick chip driving 4 LEDs. Right? Let's say those 4 LEDs are a traffic light and a stop-go for a pedestrian. And they're going to go through a sequence. And I don't know what's going on because some of the LEDs aren't working. So I decide to take the scope to it. I want to know if the scope's drawing current. So what I'm going to do is I'm going to put an extra resistor in there, a 0.1 ohm resistor. 0.1 ohm, as I say, is 0.1 of a volt per amp. So at 20 milliamps, which is what 4 LEDs would draw, I'll see a 2 millivolt difference. And if I take 2 millivolts off that 5 volt line, it won't matter a damn. If I put 4.998 volts into that pick chip instead of 5 volts, it won't matter a toot. But that lets me put my scope on the top of that pick chip and actually observe the current in that pick chip. As the voltage goes, the current goes up and down, so too does the voltage. And I can see the current. As each of the LEDs switches on and off, I can see the current going up and down. However, I want to reiterate something that I spoke about earlier. If I just take my scope probe and put it across R5, remember R5 is 0.1 of an ohm, and if I put the clip of my scope probe at the bottom of R5, that's me shorted out that 5 volt supply with a 0.1 ohm resistor. 5 volts at 0.1 ohm is 50 amps. If you've got a power supply that can supply 50 amps, then it'll just destroy the wiring. But more likely it'll destroy the power supply or make the power supply cut out. So you have to be careful with the earth in your oscilloscope. You really have to. If you take nothing else away from today, remember about earths. So I'm going to blast quickly through some measurement techniques. And I'm going to use the quick reference model. When you're learning to fly, you use a quick reference handbook all the time. It's a spiral bound set of laminated cards, and you've got one for your taxi checklist, and you've got one for your takeoff checklist, and you've got one for your post takeoff checklist, and you've got one for your engine failure checklist, and you've got one for your controlled slide into the ground checklist. Whatever you're doing, you've got a checklist to make sure that all the right settings are in all the right places to give you the best chance. And I'm going to use that model now for some of these basic measurement examples. So let's start with the DC voltage. Here's a quick reference page for the DC voltage. Estimate what you're going to do. Let's say I'm looking at a signal that's about 12 volts. 12 volts, I've got 8 vertical divisions in my scope, so I'm going to set it to about 2 volts per division. Right, so that should 2 volts per division. I should see 6 divisions of change. That'd be good. I'll put the trig on auto so that I'm getting a straight line across the screen no matter what. I'm getting the spirograph. I then ground the scope probe using the switch, put it to ground. So I'm now getting a straight line across the screen at 0 volts. So what I then do is I'll move that 0 volt line down to the bottom of the screen. Having got that line where I like it across the bottom of the screen, I'll disconnect the probe by putting it back to DC. I'll probe the voltage, and I'll read the number of divisions. Let's say I get 5.7 divisions. 5.7 divisions, I've said it's at 2 volts per division, so 5.7 times 2 volts is 11.4 volts. Let's see how it's done. Channel 1 I've set to 2 volts per division, and I've grounded it. And my trigger I've set to automatic on channel 1. So now it's triggering and it's drawing a line, and I swizzle that line down to there. That's 0 volts now from here on out. Then I switch my input to DC. I leave it on auto. I connect the scope probe to the circuit and it moves up there. Having moved up there, I measure from there to there, 5.7 divisions at 2 volts per division is 11.4 volts, which is fine. Let's do another one of these quick reference pages. I want to measure an AC voltage. I guesstimate what it's going to be, let's say about 0.6 of a volt, base of a transistor, say. So I select a sensible volts per division. Again, let's say about 0.1 of a volt. Trigger to auto ground the scope. Trigger to auto ground the scope is one of those things you do a lot. And then using the Y position, I set it. But this time it's going to be AC. It's going to be either side of 0. So I'm going to put the Y position at the middle of my screen. And at that point, I unground it. I put the voltage on. And because my trigger's still set to auto, I'll see a spirograph pattern. So at that point, I set the trigger to normal and adjust the trigger for a stable display. I read the voltage and we're done. So if you look, the knob has now moved round to 0.1 of a volt per division, and I'm grounded, and I'm triggered on automatic. I move the line up to the centre of the display. At that point, I put it onto AC. I put the triggering to normal, and I adjust the level to get the signal to catch. The signal stops moving. I pick a spot so I get a nice, easy to read waveform. I know that that line there was where my 0 volts is, and so that there is going to be from one peak to the other peak is 5 divisions at 0.1 volts per division, so it's going to be 0.5 of a volt. I guessed 0.6, so it's a wee bit less than I thought, but that's all right. I want to measure ripple. I've got a DC voltage and it's got a tiny AC signal on it, and I want to characterize both of them. So what I do is I'll set the input coupling to DC, set it to auto. See that? Trigger to auto, coupling to DC, exactly as before. I set my DC voltage, I set a 0 volts line, and I measure the DC voltage. I then go back to AC, I trigger it normally, but now I have to turn the thing up. Where I was doing 10 volts per division or 2 volts per division, I'm going to turn it up to 0.1 volt per division so that the signal is on the screen at a decent one, a decent display, and then I can read it off. So I set it to 0 volts. I've just put that red line in there to let you see that that's where I did it. There's my 0 volts at the bottom. I've got it on AC coupling. I've got it on automatic. Got it triggered, and there's my DC voltage there. I can measure it off. It's about 12.8 volts plus some ripple. And at that point, I turn the volts per division knob around to 0.1. I turn the triggering to normal, and using the level, I adjust the level till I've caught the signal. And once I've caught it, I can read off, I reckon that's 2.5 divisions at 0.1 volt per division is 0.25 volts. So I've got 12.8 volts plus 0.25 volts of ripple. Frequency. I'm going to use the same quick reference page as I just used for measuring AC. And then once I've got it done, I will use the time base so that I've got one cycle of the waveform visible on the screen, like that. The trigger can be used to move things left or right. And now, instead of using the vertical scale, I'm using the horizontal scale. So I'm measuring, let's say, from the top left-hand corner to the top left-hand corner, or the bottom right-hand corner to the bottom right-hand corner. It doesn't matter, as long as I measure from the same point on the waveform to the same point in the waveform. If I get it as big as I can on the screen, then I get the most accuracy. If I try to measure something and it's a tiny wee picture, then I'll make a guesstimate and it'll be a factor of 2 out. Whereas if I make it as full screen as I can, I get the most accurate measurement. And then once I've done that, I simply go to the time per division. Right here it's on 0.2 microseconds. So 0.2 microseconds times 5.8 is 11.6 microseconds. And if I do 1 over 1.16 microseconds, my bad, my maths, then I get 860 kilohertz. If I want to compare two signals, then I'll use the quick reference page for the AC signal again, and I'll set up the first trace. There it's there. I've set up my first trace, everything looks good. At this point, I will use the sensitivity and turn it down to make it a half, and that makes everything smaller. And then I'll shift it up to the top half of the screen. So there's my trace captured. Notice the volts per division, instead of being, it's now at 2 volts per division, I'll turn it to 5 volts per division. And once I've turned it to 5 volts per division, I can move the picture up to the top of the screen. Once I've done that, I can then switch on the second trace. I can set my 0 volts as I did before, just below the centre line this time. I don't trigger it on the second trace, I trigger it on the first trace. So there we are, I'm still triggered on the first trace. I've got a 0 volts, I put a little yellow mark for 0 volts for both of these. The 0 volts for the top trace there is on the centre line of the screen. The 0 volts for the bottom one is near the very bottom of the screen. So I've got two 0 volts on the screen, and I can read the voltages and the frequencies and all that good stuff off of these two signals and compare them and see if they're happening too quick or if there's not enough pulses or whatever it is that I have to do. And I think that's enough. I think that's 4 or 5 of those quick reference cards, and that's enough to get you using your oscilloscope to a fair level of competence. So at that, we are finished. Any questions, any thoughts, any comments?